Hello, my name is Hyunjung Kim. I'm a researcher at National Institute of Aerospace who's working at NASA Langley Research Center. Today I will give a presentation about phase-changing material-based actively tunable mid-wave infrared thin film bandpass filters. Mid-wave infrared wavelength is a spectral fingerprint for many chemical species. Multispectral filter, which covers MWIR wavelength, has wide-ranging imaging and sensing applications, from probing molecular vibrations in chemical species to detecting radiant thermal signatures. And the accurate records of chemical species such as aerosols, ozone, and carbon dioxide are a vital piece of the puzzle regarding the climate change. Especially radiometric measurement is the basis of thermal sensing and imaging and is an important component of NASA space missions. The SciFly team at NASA Langley Research Center requires an ultra-fast tunable filter for remote IR thermal measurement of the base heat shield of the booster rocket core stage for use during an observation of the Space Launch System. The accurate temperature measurement used to validate the thermal protection system and potentially reduce the required thermal protection system mass for future flight. The state-of-the-art thermal imaging system employs a high-speed filter wheel to make spectral measurements. However, such filter will offer only discrete transmission windows and has a number of filters limitations that can be accommodated. Finally, the project needs actively tunable filter, such as probing more than a single wavelength and operating across the wide wavelength band from megahertz to gigahertz, tuning speed to increase temperature measurement accuracy. Here, we introduce phase-change tunable filter. It's named PCTF, which permits actively tunable spectral filter across the MWIR waveband from a single and all solid-state element. This is achieved through the integration of the non-volatile phase-change material into filter design. This smart spectral tuning technology aims to overcome the limitation of the widely utilized polarized filter wheel by increasing spectral and temporal resolutions. And the single smart component would reduce the size, weight, power, and cost metrics because the innovative approach does not require the bulky moving parts and numerous mechanical components. This technology subsystem is underpinned by the unique electro-optics of a non-volatile phase-change material again, which exhibit a large reversible refractive index shift through applied energetic pulse. The phase-change material was developed for reliable and non-volatile memory applications for PC and DVD writer. It is because the PCM exhibits different electrical properties when switched between crystalline and amorphous phases, with reversible and linear phase transition over many cycles. Now the PCM, again phase change material, called as PCM, is transitioning from purely a memory storage media material to a multifunctional optical material from the discovery of the large refractive index contrast in 2014. As you see in here, this image is one of the PCM germanium antimony telluride 225 composition ratio, it's named GST, shows a large refractive index about 2.4 between phases, amorphous and crystalline phases across the 1, to 10 micrometer wavelength range. Exploring the large refractive index contrast between disordered amorphous and ordered crystalline states of PCM gains interest as actively tunable optical filter, such as fabric parallel thin film filter design. By integrating GST on the PCM, we can rapidly tune the filter's center wavelengths, which was impossible with existing technology. Here, the filter response depends on the crystallization state of PCM, which is subsequently or continuously tuned through differing partial crystallization using a nanosecond laser pulse or electrical pulse. The reset pulse is then used to revert the filter back to the original amorphous state, thus allowing for repeatable operation. Through adjustment of the PCM crystallinity, changing its refractive index, which is optical property, and spectrally shifting the filter center wavelengths with nanohertz or megahertz or gigahertz modulation speed. We have successfully demonstrated the spectrally tunable all solid-state filter by utilizing the GST-PCM as a tunable cavity medium of the Fabry parallel multi-layer design, as you see here. And germanium and silicon are selected as the distributed Bragg reflector materials, and with the calcium fluoride as the substrate, as you see in this image. A nanosecond pulse laser provides the stimulus for induced index modulation of GST, one of the PCM. The induced PCM index modulation increases the cavity's optical path length, thereby tuning the center wavelengths of the filter from different states of GST. The center wavelength of the filter has been tuned between 4.4 to 4.2 and 4.9, you see here, based on the GST states, either it's amorphous or crystalline states. This fabric parallel multi-layer filter is further improved through the optimization of additional layer to suppress this subband and enhance the filter resolution. This image, left image, compares the N number is 6, which means 12 layers of germanium and 12 layers of silicon filter design. The initial amorphous GST state has a center wavelength, again, is 4.5 as designed with 75% transmission efficiency. And the crystalline GST state center wavelength shifted to 4.75 micrometer with a 60% transmission efficiency and slight increase in FWHM to 65 nanometer. This is corresponding to a Q factor of 70 to 90 as the 1-inch diameter size filter. By using the 1-inch size filter, we demonstrate the multispectral thermal imaging and dynamic gas sensing by matching the filter's passband to a carbon dioxide vibrational absorption mode. This is the setup for the thermal imaging, and this is to filter for the imaging. The filter design is identical, and the difference is the PCM state. One filter is amorphous state and the other one is crystalline state. As you see here, the center wavelength of filter is different based on the PCM state. Actively tuning reliability test is ongoing, and this is not the real data. This is animated video, which we expect through this test. We did the carbon dioxide gas sensing, again by matching the filter's passband to a carbon dioxide vibration absorption mode. As you see here, when the CO2 gas is flowed through this nozzle in the left side, only one filter, which is matched to the carbon dioxide vibration absorption mode, can detect the CO2 gas flow. We also did a multiple wavelength tuning capability by using this PCM filter. The tested value is well matched with the calculated value. Our current phase change tunable filter and PCMs were launched to the International Space Station (ISS) in February 2021 this year for 6 months of staying and testing as part of the materials International Space Station Experimental, which means it's named as the MISSI project, MISSI mission. So this sample again will launched to the space for 6 months test. This is the summary of this research. Phase change material were developed for reliable and non-volatile memory applications for PC and DVD writer in 1960. From 2018, the team at NASA and outside collaborator used the unique electro-optics properties of phase change material, which give it a large reversible refractive index shift between two phases. By using the 1-inch diameter Fabry Perot multi-layered PCM filter, we demonstrate in situ control of tunability through reversible cycling, and thermal and gas detection demonstration has been fulfilled. The filters exposed at International Space Station in February this year will provide data for reliable components used on space. We are working on application-specific filter design and material selections. Material selection scenario development, such as greenhouse gases, remote sensing for LiDAR applications, and thermal signatures of the space vehicle. For the application-specific filter design and material selection scenario, we introduced the toolbox concept. The goal of the toolbox-based optimization process is to design, optimize, or tailor the tunable optics device from enough computational resources of the materials, structures, and application database. The enough sufficient resources it's like many books in a library. Uses a mix and match toolkit to form a complete device design based on the custom performance spec. As the first step for the enough phase change material resources, we introduce the PCMnet like this web link. PCMnet is online data of the complex refractive indices of the variety of PCMs such as GSD, GSST, and SBS. It is an accessible and indexed storage for data sharing across the PCM and material community. Here is what you expect to see from the PCMnet webpage. Refractive indexes and indices and extinction coefficients between amorphous and crystal states of PCMs are collected from various resources. It includes experimental data, direct extract from academic research paper, data contribution from community collaborators, and computationally generated data by using commercially available allometry software. The main object of this effort is to generate the PCM database to facilitate the selection of the most applicable PCM materials, phase change materials, depending on the application spec again. The team is looking for a highly motivated postdoctoral researcher who will develop actively tunable optical filters based on phase change materials for use in imaging spectroscopy applications. If you are interested in the position, please visit the MPP webpage, which is NASA postdoctoral program webpage, as indicated here, and search by the opportunity ID number 19345, again 19345. I would like to express my deepest appreciation to my research and engineering team at NASA Langley Research Center and outside collaborators. The project has been funded by NASA IRAD Internal Research and Development Program from 2018. If you have any questions and comments, please feel free to contact me through this email address.